the lecture 12 in the series of acoustic materials and metamaterials. So this week we have began our discussion on the different types of acoustic materials, or to say noise control materials, that are available with us. So we began with the discussion on the traditional acoustic materials, and we studied in the last class that usually the materials for noise control, they can be classified as barriers, enclosures and sound absorbers. So today's class will be the discussion on the first type, that is the enclosures. So outline of the course is, before we begin the discussion on the enclosures, I will give you a brief description on the different types of sound field that are available, because this knowledge is essential for deriving the performance of enclosures. Then what is acoustic enclosures, and then we will use a particular sound field model which is called as the diffuse sound field model for the enclosures. And then we will derive the equation for the performance of source enclosures and for the performance of personal enclosures. So different types of sound field exist. So we have studied that the sound wave, it propagates, and we have derived the equation for a linear acoustic wave equation for sound wave propagation in fluids. But this sound wave which is generating from a source, and then there is a receiver at some other end, then this sound wave can either directly reach the receiver through the fluid medium without any obstruction, or it can also reach the receiver through reflections from the other pathways. So let us say if we have a source here, so this is some source that is generating noise, and we have some receiver. Then it can directly reach the ear of the receiver. This becomes the direct field, or we call it as free field. So this is reaching the receiver directly. Then we have then suppose it is contained within some room or within some environment, and we have some reflecting surfaces all around it, or we have trees, animals, stones, any other object that may be present in the environment. Obviously when we are living in the earth, we will have so many objects around us, it won't be completely empty. So the same sound can then bounce off these different objects and then reach the observer. So this becomes the reflected field, or we call it as diffuse field. So these are the different ways through which sound can reach the receiver, and based on that we define two different types of fields. So first acoustic field we define is that, so experimentally we can create an environment which is like a complete open field. So all the obstacles and objects are removed, so that the maximum or the majority of the sound that reaches the receiver is actually the direct sound, which hasn't reflected from any other surface. Or experimentally another field can also be created. So let us say some measurement needs to be done, so we can have a room specifically designed which is called as a reverberant room. So in that all the floors, the ceilings, the walls, etc., everything is a hard reflecting surface. So there is no absorber, there is all hard reflecting surfaces around, and there are many such oblique surfaces as well, not only parallel. So in that case what will happen is that any sound that is generated within that particular environment, it will reach the receiver directly, as well as it will have some countless other paths to reach the receiver by bouncing off other reflecting surfaces. So these two type of fields are free field and diffuse field. The definition is as I have already given you. In the free field, it is that region of space where sound propagates freely without any form of obstruction and without any reflection, and it reaches so in this case any sound wave, it will reach the observer just once directly, and it will pass through the observer exactly once, and it won't return back. So there won't be echoes or reflections. So in most of the cases when the sound is placed in a very far away area, or there are no nearby obstructions, then this can be achieved. And in such fields what we assume is that if suppose the dimension of the source is small compared to the other dimensions like the distance of measurement, etc., So in that case, in the free field we assume that small sources, they have spherical wavefront. So we assume them as point source and they are giving away spherical wavefront. Whereas if suppose the same source becomes too far away, for example, suppose a person is standing in a free environment and then there is a jet aeroplane that is passing at quite a significant height. So in that case, then the jet airways or the plane, it will emit a spherical wavefront, but by the time it reaches the receiver, that can be treated as a plane wavefront. So if the object is here and the receiver is here, so it's this is a point object, it is radiating radially outwards. So the sound is being emitted radially outwards and the spherical wavefront is reaching the receiver. But when the distance is too far away, if suppose we have the receiver here and the source too far away, then that same spherical wavefront that was being generated, after a certain distance it almost appears parallel, like a parallel wavefront as the radius of the sphere increases. The second type of field that we discussed, that I mentioned, was diffuse field. So the definition here is that the sound waves in this particular field, they reflect numerous times and reach the observer from all the directions. So if we have one observer here and the sound may be present here, but it can reach here, it can bounce from here, it can bounce from here. So there are many obstructions and it can reach the observer from various paths in all the directions. And the magnitude of these reflected waves is almost similar to the magnitude of the direct wave. So in that case, if the listener has his eyes closed and the sound is reaching from all the directions, so for him it's like an omnipresent sound, it is sounding the same everywhere and the listener cannot make out where the noise source is. So this is called as a diffuse field, where we have there are numerous such reflected waves that overall the waves are present throughout, there is no directivity. And in such a field, what is an important assumption is that if you place a microphone within such diffuse field, then it will measure the same magnitude regardless of what its orientation or location is. Because let us say if we place a microphone that is oriented here, it will measure the same, a microphone here will measure the same, because the reflected waves are almost as strong as the direct wave and they are present everywhere at every location. So in that case, for a perfect diffuse field, the SPL is the same everywhere. So both the SPL and the acoustic intensity, SPL and therefore the acoustic intensity remains uniform throughout the diffuse field. Okay. Then there is another distinction that is called as a near field and the far field. So near field is the field of a sound which is very close to the source, almost of the order of one wavelength. So let us say there is a source emitting a sound which is having a frequency of 100 Hz at air at room temperature, then we can assume the speed of air is 340 meters per second. The corresponding wavelength of that particular sound will be 340 by 100, which is 3.4 meters. So within that particular domain of 3.4 meters around the particular sound source, it will constitute a near field, and beyond that distance will be the far field. So if we have a source which is emitting sound over here, then up to lambda, up to a distance of lambda, let us say, we have near field, and beyond that distance everything else becomes far field. So the peculiar thing, why do we study about this near field and far field, is that, so we have this as far field. So why do we distinguish it as near field and far field, is that the wave propagation equations that we have studied till now in this course or in acoustics in general, they all apply to far field measurement, because everything has its limitations. You cannot, any instrument, it cannot measure proper waves within the near field. It can only measure in the far field, because there the sound waves takes the full propagating wave front. So whether it is a plane wave front, which is defined by a e to the power j omega t minus kx, or whether it is a spherical wave front defined by a by r e to the power j omega t minus kr, and so on. So all these equations, they are only valid for far field, but within the near field, or when the receiver or the point of measurement is extremely close to the source within a wavelength or so, in that case what happens is that as the surface is vibrating, so there is a vibrating surface that is generating noise. So as a surface is vibrating, some of the air molecules, it will touch it, it will try to go and propagate away, whereas some air molecules, they will just oscillate back and forth, there will not be any propagation. So it will constitute the waves which do not propagate, they just decay over time, and it will also constitute of the waves which are strong enough and they propagate away. So within the near field, we do not get exactly fully propagating wavefront, it constitutes propagating wavefront as well as the decaying wavefront, which is called as a evanescent waves or evanescent field. So I am discussing this near field here. Why? Because any measurement that is being done is not done within the near field, but it is done in the far field. So after just a brief discussion of what is meant by these various sound fields, we will begin with a discussion on acoustic enclosures. So acoustic enclosure, as we have defined previously, these are path based noise control. It is designed to contain, confine, or simply encapsulate the sound source or the receiver, and they are usually made up of some hard materials which can reflect or block most of the sound. They can also be designed to dissipate more, but the main idea is that this is the main idea, which is to transmit less. So this is the main idea, that it is made up of materials that can block the sound or bounce the sound away and not allow the sound to pass through it. So that is the main metric of, that is the main purpose of using an enclosure, to block the sound and not allow it to pass away. So the performance of such materials is measured using the metrics like noise reduction, transmission loss, and insertion loss. So let us see. Now an enclosure can be complete. So usually by enclosure what we mean is that it is completely enclosing a particular sound source or a particular receiver, but it can be full or it can be partial. So sometimes small openings are given within an enclosure. Why? For example, for a source enclosure, suppose some machinery needs to be enclosed from the surroundings, then some small opening or doors or windows can be provided, because the machine may need some timely maintenance, and therefore some opening needs to be given for timely maintenance or for cooling down the machine. Similarly, in the case of a personal enclosure, some openings or windows can be provided within the enclosure, that is just so that the receiver or the personnel who is working in a plant, he does not suffocate, and he can, there's sufficient ventilation, and he feels comfortable and convenient within the enclosure. So small openings can always be provided within the enclosure. So when these small openings are provided, so in that case obviously the performance of the enclosure will reduce quite a bit, because the openings will allow all the sound to pass through, they will be like complete, so they will reduce the overall transmission loss of the enclosure. So if we begin the performance of the two types of enclosure, that is the enclosure for the source and the enclosure for the receiver. So in that case, the assumption that we make here is that it is a diffuse sound field which exists within the enclosure. This is the assumption. So here, first of all, it is ensured that the enclosure should be big enough that that the walls of the enclosure, they do not lie within the near field of the machine source. So in that case, a smallest distance between the machine surface and the enclosure walls must be greater than the wavelength that is being targeted, so that the walls, they do not lie within the near field of the source. And with this is one precaution that's always taken. You cannot have too small an enclosure, so that the walls of the enclosure, they lie within the near field. So, at least one wavelength distance has to be maintained between the machine surface and the enclosure wall. So now we have a closed tomb or an enclosure, and as we know that it is made up of material that reflects most of the sound, it does not allow any sound to pass through. So the environment within the enclosure will contain the direct field that is propagating away from the sound, as well as the field that is being reflected from the walls continuously. And because the enclosure is completely surrounding the source, so there will be numerous such reflections. So the enclosure, which is a good reflecting material, will reflect a lot of sounds, and the source will also pass on the sound, and there will also be the reflections from the sound. So overall, in steady state condition, the field within an enclosure becomes a diffuse field. So this is what happens in the steady state. The sound field inside an enclosure is a diffuse field. So now that we have established the rationale for why the sound field within an enclosure is diffuse field, we can easily solve and find out what is the performance of an enclosure. So in this kind of diffuse field model, the intensity, the acoustic intensity and the acoustic pressure will be uniform within the enclosure, and it will be the sum of both the direct and the reflected fields. So let us begin with source enclosure. So we are here, I have shown in this figure is that there is a source, it is being enclosed here, and there is a receiver outside, and the noise is being generated here. So here some power, so here this source is generating noise, so some sound power will be incident on the enclosure walls. So let the power incident on the enclosure wall be given by W1. So because the field inside this is diffuse, this is a diffuse field, and this field itself is a diffuse field. So there is diffuse field throughout. So under steady state, there will be a uniform intensity within the enclosure. Let us say that intensity is I1. This is the intensity that is being incident. Then the power incident on the enclosure becomes the intensity multiplied by the surface area. So whatever power is radiating, that power is being incident on a particular surface area. So it is the incident intensity, or the intensity of the wave that is incident on these walls multiplied by the surface area will give you the power. Here this is the internal surface area of the enclosure, and this is the intensity that is incident on the enclosure. So I1 into SE. Similarly, the power that is being transmitted by the enclosure. So some power was incident on the enclosure, that was W1, and after reflection some amount of energy may pass through the enclosure walls. So whatever sound power that is little or more, whatever sound power that is being transmitted from the wall. So the power that is actually being transmitted from the wall will actually be absorbed under steady state, or after a sufficient amount of time. This entire power that is being transmitted will now be absorbed by the outside room. So it will eventually get absorbed by the outside room. So we can simply say that whatever power was transmitted is equal to the sound that was eventually absorbed. So W2 becomes I2, which is the, this is the, here out I2 is because we have a diffuse sound field here also. So in this case, whatever is the uniform intensity which is being incident on all these, on the walls of the receiving room. So this intensity multiplied by the surface area of the receiving room multiplied by the average absorption coefficient of the receiving room, this together gives you what is the total power that is being absorbed by the receiving room. And after sufficient amount of time, whatever sound that was transmitted, whatever power that was transmitted from the enclosure will be getting absorbed. So this becomes the expression for W2. So now that we have the expression for W1 and W2, and we know that the intensity 1 at any time is directly proportional to P1 square, I2 is directly proportional to P2 square, and what we are assuming is that both 1 and 2 have same fluid medium. So rho c becomes constant and it is directly proportional to pressure square. So if it is air inside, then there will be air outside also. This is the basic assumption we are making. Then the transmission coefficient or the intensity transmission coefficient tau can be given by, it is, tau is defined as the intensity that is transmitted from a particular material divided by the intensity that is incident on the material. Now we do not know the exact intensity that was incident and the intensity that got transmitted, but we know their steady state values, that is I1 and I2. So because now we do not know that exact intensity which was incident and transmitted, so we take this ratio as the ratio of the power. So tau now we can take as W2 by W1, which is P2 square S2 alpha. This is the expression for W2 we derived, and this is the expression for W1 that we have derived in the previous slides. So these are the two expressions we have derived. So this is the expression ultimately which we get. Now if we take 10 log 10 from both the sides, so we get 10 log of tau becomes 10 log of P2 square by P1 square plus 10 log of S2 alpha bar by SE. Again P2 square by P1 square, if you divide the numerator and denominator by P reference square, then this is the expression. And as you see this numerator part, just have a look at the numerator part. The numerator is 10 log, so you can separate this into two parts. This can be separated as 10 log of P2 square by P reference square minus 10 log of P1 square by P reference square. So by the property of log, the numerator by denominator can be separated like this. So we have separated the numerator and denominator. So this entire quantity is what it is. This is LP, this is the SPL at field 2, this is the SPL at field 1. So it becomes LP2 minus LP1. So this expression becomes LP2 minus LP1 plus 10 log of this expression. So now taking the quantity on the other end, what we get is LP1 minus LP2 is minus 10 log tau plus 10 log of this expression. And minus 10 log tau is 10 log of 1 by tau, and we know that transmission loss is defined as 10 log of 1 by the transmission coefficient. So by the definition of transmission loss, we have discussed about its formula in our previous lectures. This can be written as the transmission loss. So overall the difference in the sound pressure level from medium 1 to medium 2 is the transmission loss of the enclosure material plus 10 times the log of the surface area of the receiving room into the average absorption of the receiving room divided by the surface area of the enclosure. So this is the particular case. Similarly, we can find out what is the difference between the sound pressure level in case of a Parsonal enclosure. So now we have enclosure where it is enclosing the Parsonal. So here the sound is being radiated from here, and this sound then gets incident on this enclosure walls, and the sound that gets transmitted then gets transmitted here. So the whatever sound is incident can be written as the intensity into the surface area over which that intensity is incident. So we take the steady state or the uniform intensity I1 into the surface area of the enclosure. So whatever sound is incident on these enclosures. So W1 becomes I1 into SE, and then so whatever sound was incident on the enclosure, some bit of it will get transmitted into the receiver's room or the Parsonal's room. So when this sound is transmitted into the receiver's room, again assuming that after sufficient amount of time has passed, there is a steady state condition. So whatever sound is getting transmitted is eventually getting absorbed within the receiver room, provided we have some sufficient absorbing materials present within the receiver room. So ultimately whatever sound that was transmitted will gets absorbed within the room. So this can be written as the total sound absorbed, which is the intensity that is present within the enclosure into the surface area of the enclosure multiplied by the average absorption of the enclosure walls. So here the difference between the source and the Parsonal is that in the source case the energy was incident on the enclosure and then it was transmitted to the receiving room. Here The energy is again incident on the enclosure and then it is transmitted to the receiving room, but the receiving room and the enclosure, they both have the same surface area. So, the surface area for receiving and incident both becomes the same. So, this was the W2 and W1 expression. Now, taking that, tau can be written as W2 by W1, the same logic. So, here SE cancels out and this is the expression we are left with. Now, if we take 10 log 10, then this is the expression we get, P2 square by P1 square plus 10 log of alpha bar. Okay, SE has already cancelled out. So, again dividing the numerator and denominator by P reference square, then separating them with respect to the property of log, just the way we did for source enclosure. Overall what we get is, this expression can be written as, this particular expression 10 log P2 reference by PR reference becomes the LP2 and this becomes LP1. So, this entire thing becomes LP2 minus LP1, or the SPL at the field 2 minus the SPL at the field 1. And then again taking it in the other end, we get the net difference in the sound pressure level is given by the transmission loss of the enclosure material plus 10 log alpha bar, where alpha bar is the average absorption coefficient of the receiving room. So, to sum the performance, now we have derived what is the expression that we have derived is what is the difference between the sound pressure level after it passes through the material. So, before the material, the SPL before passing the material minus the SPL after passing the material, and by definition this becomes noise reduction. So, noise reduction or the performance, it is one of the performance measure is LP1 minus LP2, and the expression for noise reduction of a source enclosure is this, and the expression for this becomes this one, TL plus 10 log alpha bar. So, these are the two expressions that we have derived. So, from this what we see is that the performance is directly dependent upon TL. So, as the transmission loss increases or as the transmission coefficient tau decreases, the noise reduction will improve. Similarly, as the absorption increases, again reduction will take place. So, the overall noise control performance of an enclosure will increase with a decrease in transmission coefficient, because when tau decreases, TL is going to increase. It will also increase with increase in wall material thickness. It will decrease with openings and gaps in the partial enclosures, because if we have enclosures and some gap and opening is given, then the TL is going to reduce drastically, because for that particular area the TL is going to become 0, there is going to be no transmission loss. Similarly, as the absorption coefficient increases, this will increase, because this value is going to increase, this value will increase, so NR is going to increase. So, these are the various factors on which the noise control performance depends. So, typically as I mentioned when we were discussing about personal enclosures, is that sometimes the material, the enclosure inside, the enclosure at the receiving end is lined with absorbers, so that whatever sound is being emitted can ultimately be absorbed within the personal room. So, usually in this case, let us say we have a material, this was a blocking material. So, reflections and transmission are happening and some sound wave is getting transmitted. But if we add a absorbing material, then the transmission is going to reduce further, because after passing through the material, let us say we have some transmitted wave, but that will again get dissipated and even a lower magnitude of wave will then pass through. So, even the transmission can be reduced further if a hard material is lined with a absorber material. So, with that I would like to end the discussion on acoustic enclosures. Later in this week we will solve a few numericals based on its performance, and in the next class we will discuss about barriers. So, thank you for watching.